Welcome to ECE 302. This is lecture 2.4 on conditional probability. I am Professor Stanley Chan. Here is the outline of today's lecture. We're in the middle of the second chapter of this course, and we are now in section 2.4. In this section, we are going to learn one very interesting topic, which is about linking the relationship between two random variables or two random events. So what I want to do is to introduce the definition of conditional probability, and then I want to show you some examples of conditional probability. Towards the end of this lecture, I want to explain why the conditional probabilities will also satisfy the axioms of probability. Now, you should really treat this section 2.4 as the first part of a three-part discussion. If you look at this outline, we also have section 2.5 on independence and section 2.6 on Bayes' theorem. These will also play a very important role in terms of understanding the conditional probability. So in today's lecture, we are going to learn the basics about conditional probability. And then in the coming two lectures, after we have learned the Bayes' theorem, we will be able to solve a very broad set of problems. So without further ado, let's talk about the definition of conditional probability. Let us consider two events, A and B. Let's also assume that the event B is not an empty set. Therefore, the probability of B is not zero. We define the conditional probability of A given B as the ratio between the intersection of A and B and the probability of B. The notation for this conditional probability is written as P of A given B. So this notation really has to match of which conditional probability that you are talking about. If you're referring to A given B, then you are writing in the following way of A given B. If you are looking at the conditional probability of B given A, then the conditional probability will be written as P of B given A. Now, the conditioning, it is very important. A given B is not the same as B given A. Okay, and so this is not the same as probability of A given B. They are two different things. So let us look at the definition of this conditional probability by looking at the ratio. In this ratio, you can see it is the ratio between the intersection and also the conditioned event. Okay, so how do you visualize this problem? Well, one way to look at this problem is try to compare this ratio versus this intersection. Okay, so now let us consider two probabilities. The first probability is as A given B. The other probability is A intercept B. Now, both can be written as a ratio. For the conditional probability, you can write it as the ratio between A intercept B divided by B. The intersection can also be written as a ratio. However, the denominator is now just the entire universal set or the sample space. Okay, and so now what do you observe here? The numerator of both ratios are identical. They are both looking at this intersection of A and B. The difference is in the denominator, where in the conditional probability, the denominator is b. In the intersection, the denominator is omega. So if you want to draw a diagram, then you realize that the intersection between A and B, that's very straightforward. You look at two sets, A and B. The intersection is just someone in the middle. And then you are taking this area and then you divide by the area of the entire sample space, which is 1. That will give you the intersection. The conditional probability says that instead of just looking at this number divided by the entire sample space, I am going to take the ratio between this intersection and also whatever I want to focus on. And in this case, I want to focus on B and nothing else outside B. And so when you look at this ratio, this is A intercept B, and then here this is B, and therefore this ratio really tells you what is the proportion of this A intercept B with respect to B. That is the conditional probability. So here is a diagram. It's a better drawn diagram that shows you the difference between conditional probability versus the intersection. The conditional probability, as I have mentioned, is really the ratio between this intersection and whatever you want to condition on. Okay. All right. So this definition may appear very abstract. Okay, and therefore let us go into some examples to gain some insight about this conditional probability. Let's look at this example. There's nothing to calculate, but we can learn some conceptual idea about the conditional probability. Let us define two events, event A and event B. Event A says that I'm gonna eat 2 burgers, and then event B is the event that I finish a football game. So there are 2 events, A and B. So if you're looking at the probability of A, that is just the probability that you will eat 2 burgers. Now, this can happen regardless of whether you have played a football game or not. Okay, so that's just the bare probability that you will eat 2 burgers. For example, if you are someone who really likes burgers, then no matter what happens, you will eat a lot of burgers. Okay. Now, B is the probability that you just finish a football game. Now, that may not have any correlation with this burger or not. Okay. And then now, let's look at this intersection of A intercept B. This is the probability that you finish a game and then you eat 2 burgers. Okay, so you can visualize in this way. This is event A, this is event B. There will be certain situations where you have finished a game and then you will eat 2 burgers. So that is the intersection of A and B. Okay, now let us look at the conditional probability of A given B. This says that first of all, you need to play a football game, which is a very demanding exercise. And so now after the game, you become very hungry, and therefore you eat 2 burgers. So among this entire sample space, what you would do is that you are going to restrict yourself to the event that you have finished a football game, which is this circle of B. When this has happened, you ask, what is the probability that I would eat a burger? Okay, and so now eating the burger, that is A, but eating the burger and finishing the game is this intersection. And so when you look at the conditional probability, you are asking, well, what is the proportion of this orange area with respect to the blue area? All right, so this, I hope it has given you some idea of what this conditional probability really means. It is relating two events, event A and event B, and you assume that event A has happened, and then you ask what is the likelihood that event B will also happen. Pay attention to this word also, because you want both A and B to happen with respect to the occurrence of B. Let us look at a more concrete example. In this case, let us throw a dice and suppose A is the event that you can get a number 3 and B is the event that you can get odd numbers. So we want to ask what is the probability of A given B and B given A. Now, whenever you want to calculate the conditional probability, we need to know the intersection of A and B, and then probability of A as well as the probability of B. So let us find these three numbers out, and then we can just apply the definition, and then we will see if it makes sense. So the probability of A intercept B is what? This is just the probability of having an intersection between getting a 3 and being an odd number. And so it's just the probability of getting a 3. So that will give you 1 over 6. The probability of A, this is just the probability of getting a 3. So this is also 1 over 6. The probability of getting an odd number, this is the probability of getting 1, 3, and 5. And so this probability is 3 out of 6. Okay, so we have calculated the intersection, the event A, the event B. And then we ask, what is the conditional probability of A given B? According to the definition, this is A intercept B divided by B. And so you have 1 over 6 divided by 3 over 6. This will give you 1 over 3. How about the other conditional probability? Probability of B given A, and this is the same intersection, A intercept B, divided by the probability of A. And so that will give you 1 over 6 divided by 1 over 6. That will give you 1. Very strange. Why are you getting a 1 when you're calculating the conditional probability? Let's go back to this problem and see if it actually makes sense to get 1/3 and get 1 here. Now, the conditional probability of A given B says that suppose I have got an odd number. Okay, so among these 6 choices, okay, so this is 1, 2, 3, 4, 5, 6. I have 6 choices, and then I assume that B has already happened because I'm looking at the conditional probability of A given B. So assume that B has already happened. So that means I am really just looking at this event. This is my B. Among the B's, I want to look at what is the probability of getting a 3. Okay, and therefore you're looking at this event A, and this event is also A intercept B. Of course, in this case, that's also A. Okay, but let's just look at this A intercept B. The ratio between this A intercept B divided by B, this is clear. This has to be 1/3 because you have 3 points and then you're picking 1. Now, how about the other conditional probability of B given A? All right, so now this is B, and then when you look at the intersection, this B over A is calculated in what way? Well, B over A, first of all, this is A intercept with B, and then what is A? A is just this. This is A, and therefore the probability of B given A, this is just one choice out of one choice. It has to be 1. If you look at the definition here, what is the conditional probability of getting an odd number if you have already got a 3? If you have already got a 3, since 3 is an odd number, you are absolutely certain that B will happen. Okay, so think about this again. A is the event that you get a 3. If this has happened, then B will absolutely certain to happen. Okay, because this is an odd number. And therefore, when you look at this conditional probability, it will give you 1. This also shows you that the conditional probability of A given B is not necessarily the same as the conditional probability of B given A. Now, let us work on a somewhat more difficult problem in this example. So here is a situation where you have 12 points. They have equal probability of happening. So all these black dots, they have the probability of happening is 1/12. They're equal. And I want to find the probability of A given B, and then the probability of B given A. Okay, so in this diagram, I have 12 points, and I have circled this region to be A, and then I have circled the other region, this region, as my B. And so if I want to calculate this probability of A given B, essentially I need to find 3 probabilities: probability of A, probability of B, and probability of A intercept B. So what is the probability of A? The probability of A, we just need to go to A, okay, and then count how many points are there in A. So within this red circle, we have 5 points, and so this is 5/12. The probability of B, we can count again. We count 1, 2, 3, 4, 5, 6. So there are 6 numbers out of 12. So this is the probability of B. What is the probability of A intercept with B? Well, A intercept with B, there are only 2 dots that are living inside this intersection here. Okay, so you have 2/12. So now we can calculate the conditional probabilities. The probability of A given B, this is the ratio between A intercept B divided by the probability of B. This will give you 2/12 divided by 6/12. So you get 2/6, and this is 1/3. We can also calculate the event of B given A, and this is the probability of A intercept B divided by the probability of A, and so here you have 2/12 divided by the event of A, so this is 5/12, and so you have 2/5. Now, let us go back to the diagram and check if all these numbers make sense. First of all, let's look at A intercept B. So A given B. A given B says that I am looking at the ratio between this intersection region, and then the base that I'm looking at is B. So I have 2 points out of how many points here? There are 6 points inside this B, and therefore the conditional probability of A given B is 2/6, which is this number. We can also check the other conditional probability of B given A. B given A says that I am looking at this intersection, and then the base that I'm looking at should be A, and so I count. There are 2 points that are living in the intersection, and then 3 that are out. So altogether, I have 2/5. Okay, so let us work on one more. Suppose you are throwing a 4-sided dice, and let X be the first row and Y be the second row. let event B be the event that a minimum of x and y equals to 2, and M be the event that the maximum of x and y is equal to 3, and we want to find this conditional probability that M given B. Okay, so first of all, let us try to understand this event B and this event M. What is event B? B is the event that minimum of the first row, and then the second row is 2. Okay, so this is first and this is second. Okay, so let us do some thinking here. Suppose my x is 1, because I have 4-sided dice, so I can have any number between 1 and 4. And suppose y is 2. All right, and then I want to compute this mean operation. Mean of xy, well, in this case, it's just mean of 1 and 2. And what is the mean? Well, mean will give you 1, because the smaller number is 1. Now, let us try to replace the x, okay? So suppose now I change the x to be 3, and then y equals to 2, okay? Then in this case, I have minimum between 3 and 2. So what is that number? That minimum between 3 and 2, of course, is 2. So you can go to this diagram, and we can draw the shape of B. Okay, so I'm drawing a 4x4 array. And the x-axis denotes the first row, the y-axis denotes the second row. And then I want to highlight the event B. Where is it? Well, let's look at here. Suppose my x is 2, okay, and then my y is 1. Okay, I'm just looking at a case where here x is 2, y is 1. So I'm looking at this minimum operation. And so what is the mean? The mean is 1. And so now you go to this box, you can check, is this 1, right? So because the minimum between 2 and 1, that is 1. And is this 1 included? Well, that is not part of this event B. Okay, so we do not highlight it. Now, let's go to this case. Suppose the first is 2, the second is 2. Then you have the first is 2, the second is 2. And then you calculate the mean. That is giving you 2. And so we find that, okay, the minimum is 2. And so that is part of the event. So you draw this a green box. You can continue this experiment with x equals to 3 and then y equals to 1, and this is not part of this event. When you go to x equals to 3, y equals to 2, the smaller between these two, which is the number 2, so that is included. And you keep doing it, and you can see that whenever you have a smaller number, which is 2, that will be included. Okay, so here x is 2, y is 2, here is 3, y is 4, and all these will give you a minimum of 2. Same for these numbers. So now you have found the green boxes to represent this event B. How about this event M? The event M can be done in the exact same way. You just look at x and y, and instead of putting a mean, you put a max. Okay, so we can do a very quick experiment. Let's say you are looking at x equals to 3 and then y equals to 1. Okay, and so x equals to 3, y equals to 1. The maximum is 3 and 1, and so the max is what? The max is 3, because 3 is bigger than 1. And so now you check whether this M, this is the event. The event is max equals to 3. So this is inside this event M. Okay, so then you go along this line, then you can check all these green boxes. So now we know that the blue boxes, they represent the M event, and then the green boxes represent the B event. And so to calculate this probability of M given B, we just need to find the intersection of M and B divide by the probability of B, because this is really the definition of the conditional probability. So what is the probability of M intersect with B? Well, M intersect with B, it would be clearly here and here. So you have 2 out of 16 boxes that are checked by this intersection. Probability of B will essentially be anything that is green. So you have 5 over 16 here, and therefore the result is 2 over 5. That is the conditional probability of B, M given B. I hope with these examples you have seen the way to calculate the conditional probability. Now, before we finish this lecture, let me also comment on the fact that the conditional probability will satisfy the axioms of probabilities. And what do I mean? Here is the proposition. Assume that the event B is not empty, so that probability on B is bigger than 0. Then the conditional probability of A given B satisfy the axiom 1, 2, 3. So let me show you why this is true. The axiom 1 says the non-negativity. Okay, and so if you apply this probability of A given B, this is a conditional probability on B. So B is assumed to be fixed and known. So you're conditioning on B only. Okay, and this is giving you the intersection of A and B divided by the probability of B. And you can see that this, by construction, it is positive. It's also true from your assumption here. And what is this? This is just certain events in your sample space, and by axiom 1, this has to be bigger than or equals to 0. Okay, so when you take this ratio, then certainly this thing has to be bigger than or equals to 0, and therefore you have this result of the conditional probability of A given B has to be bigger than or equals to 0. So that is axiom number 1. Now, axiom number 2 says that the probability of omega is 1. And so now if you're looking at the conditioning side, then you condition on B. And we want to show whether this is giving you 1. And it's fairly straightforward because this is the ratio between omega and B divided by the probability of B. And what is the intersection between omega and B? That's just B. And so when you calculate this B divided by B, that will give you 1. And so that has verified the axiom number 2, which is the normalization property. The third axiom says that the for any disjoint set, you can when you take the probability of the union, then you can add them up. And so what we want to show in axiom 3 is that the probability of A union C given B, okay, B is still the fixed event, and then we assume that A and C are disjoint. Then we want to show whether this is true to have probability of A given B plus the probability of C given B. If it holds, then we can show that this conditional probability will satisfy axiom number 3. Now, this is also not hard to show because this is just the probability of A union C intersect with B divided by the probability of B. And so we can do some set operations in the numerator. So that would give you A intercept B union of C intercept B. And then you can still have the denominator of probability of B. And now note that this is the intersection between A and B. Here is the intersection of C and B. But your C and A, they are disjoint already, and therefore there's no way for these two to have any overlap. And therefore, by axiom number 3, you can write it as the probability of A intercept B plus the probability of C intercept B divided by the probability of B. And then you can show that this will give you this probability of A given B, because that's just the ratio between this A intercept B and B, plus the probability of C given B. Okay, so now we have shown that the conditional probability also satisfies the axiom number 3 of the probability. So this is the end of this lecture. Conditional probability will play a very important role in our subsequent studies. So I encourage you to take a look at the lecture notes and also try the homework exercises on this conditional probability. If you have any question, please ask us. We'll be here to help you. Thank you.